Welcome back. In lecture 12, we will cover sampling theory part 2. The concepts that will be covered in this lecture are on sample size, variability of population, degree of precision and confidence level, population parameter estimation method, and within that sample size for mean and sample size for proportion. So, when we in the last lecture we have discussed the different procedures for collecting samples or procedures for surveys. So, in this lecture we will cover different ways to calculate the sample size for a particular study. So, we understand that sampling error reduces with the increase in sample size. That means because we are using a sample instead of the total population, so any estimate that we do with the data, for example, if we try to find the central tendency, the mean or the standard deviation, it is going to be different from the population or the total or the samples parameters are going to be different from the population parameters. So that means there is some error in the estimate. So this is called sampling error, and the more is the size of the sample, this sampling error gradually reduces. But that again, if I increase the size of the sample, it will incur more cost or higher resource for that particular survey, and we will incur both time and cost. And so we need to find the equilibrium between these two extreme conditions so that our sample is more or less accurate, precise, whereas at the same time it is not too large, so that it is almost so that we can reduce on the number of households or number of individuals that we need to survey. Sample size determination is not only based on statistical criteria but also on financial and logistical constraint. Now, sample size we can based on formula we can determine sample sizes, but it may be the number of samples that needs to be collected may be beyond the financial capability of the surveyor. That means, or the resource for that particular study is we don't have so much resource or money for that kind of survey collection, sample collection. So that is where we need to be careful, or we can also reduce a little bit of the sample size following certain strategies, following certain procedures. So only the statistical criteria is not enough. We also need to consider about the logistical, that means if that kind of sample can be collected or not, and the financial criteria as well. So in the comprehensive mobility plan lecture, we have earlier discussed that around in Indian condition, because our cities are pretty dense, around 1 to 2% of the population can be surveyed for household surveys when we are doing any kind of travel diary or this kind of service. But in general, our rule of thumb could be said that around 10%, if it's for a smaller population or a subgroup of a population, we can stick to around 10% of the total population, and that is good enough, provided it doesn't exceed around 1,000 samples or so. So that means we can set a higher limit as 1,000 or a limit of 10% of the total population that we are going to survey. So 1 to 2% when we are looking at the entire city in an Indian context, probably a large or a medium sized city, but in case of small cities or for specific surveys, we can also target 10% of the total population. So there are two ways we can determine sample size. Primarily, there are two ways. One is called population parameter estimation method, and the other one is hypothesis testing method. Now, population parameter estimation method is based on precision. Now, precision means with what precision measurement a study needs to be done. That means whenever we are doing a sample, how much precise should be my final results would be. So that is something which is very, very important. Or rather, if I have a sample, I estimate a mean for that particular sample, how precise should be the estimate of the mean from the actual estimate of the mean of the population. And the other one is hypothesis testing method, which is based on the power. And what it means is, first of all, hypothesis itself, the term means that we have two data sets, and we test them or compare them to find any sort of statistical relationship in between these two data sets. If there is no relationship, then we say that the null hypothesis is validated. So this is when we do the hypothesis testing, and from there also we can determine what kind of sample size is determined. And power basically means how small a difference should be detected and at what degree of certainty. So this is where it talks about that, okay, what should be the difference between those two population groups that we were testing earlier. So that is what hypothesis testing method is. But in this particular study, we will not focus on the hypothesis testing method because we are primarily looking at travel diary surveys and all. So we will stick to population parameter estimation method. So sample size depends on primarily 4 factors. One is population size, then the variability of the population, then degree of precision required, and the confidence level. I will explain each of these factors one by one. So population size is obvious. That means the more is the size of the population, it may have a role on the total number of samples that is collected, but not always, because population size could be infinite, but that doesn't mean that we will collect the sample size would be of a number which is impossible to collect, means it cannot be very large. So population size do play a role in certain methods, certain formulas, or certain ways of estimating sample size, but not in all. And then variability of the population. By degree of variability actually means that the more heterogeneous a population is, it requires a larger number of samples and for the same level of precision compared to a homogeneous population. That means the sample mean is, we decide on a certain level of precision for that sample mean that we are going to for the particular sample that we are going to collect. And the more heterogeneous a population is, there is chance that we require a larger sample to make sure that the precision levels are fine. So that is why we say that whenever a group is divided into like 50-50, then the proportion, that means that it's the maximum amount of heterogeneity is being considered. If it is like 80 or 20%, that means one group is 80%, another group is 20%, then the amount of heterogeneity in the estimate would be lesser. So the population heterogeneity is actually less. So that means variability is basically lesser. So usually in many studies what we do is, if we want to go for a very a conservative sample size, that means we cannot be wrong with this kind of sample size selection, then we take variability as a fixed value of 0.5, which actually indicates it's a maximum variability in the population that is possible when we are comparing two groups. So that is that is used when we do this kind of estimates. Then talking about degree of precision. Degree of precision or sampling error arises since a sample is being used to estimate a population parameter, maybe mean in this case. So of course, because we are using a sample, the sampling error is there because the sample mean is not going to be same as the parameter mean. But bigger the samples, less is the sampling error. So you can see in this particular image, in this particular case, the sample size is 2401. And we have taken a margin of error as 2%. Margin of error is error expressed, the sampling error expressed in percentage. So if the error is 2%, that means if we have a sample mean and there is the population mean, and the sample mean should be within 2% of that in either sides, plus minus 2%, then the sample size has to be of 2401. This should be the size of sample. So if the margin of error reduces, that means it could be plus minus 3%, then the sample size also comes down drastically to only 1067 samples. And it goes on, and if I say a margin of error is 10%, the sample size required is only 96. So here we can see that, okay, and once we know that, okay, this is the margin of error, that is, if I have a mean and all the sample means are distributed like this, the more is the sample size, more tightly it would be near the actual mean. So when the sample size is large, sample means are near to the population mean. So if I have population mean at the middle, then sample means would be near to that. When the sample size equals the population size, the standard error of the mean is 0. That means it would be same as the population mean. So confidence level or risk level is determined using normal distribution and the central limit theorem. So this is a very, very important theorem in statistics. And basically when we draw samples of n items from our overall population, which may or may not follow a normal distribution, and develop the distribution of the sample means, it increasingly becomes normal as the sample size increases. That means if I plot the sample means that we have obtained, we will see that the higher we will see that the more sample means are near to the actual population mean, and it follows a normal distribution like this. And this particular curve could be defined. This is also could be defined as a probability density function, and with distribution with mean mu and standard deviation sigma, and it is given by the equation as it is shown over here. So the central limit theorem states that if x1, x2, x3 and xn is a random sample of size n drawn from any arbitrary population with any arbitrary distribution having mean mu and variance sigma square, then the distribution sample mean, which is x, is normally distributed with mean mu and variance sigma square by n, provided n is sufficiently larger than 30. So what it means is, if I draw a random sample of size n from any population with mean mu and variance sigma square, then the sample mean, if the number of sample size is more than 30, in that case, if we estimate the sample mean, it would be more or less, it would be normally distributed, and not only that, it will have the same mean as the population mean, which is mu, and the variance would be sigma square by n. Now sigma square is the variance of the population. So sigma square by n is the variance of the sample. So we can say that standard deviation of the sample, or which is also called standard error, is equal to sigma by root n. So this is very, very important, and what it shows is if I know the sample estimates or the sample parameters, then if we can estimate the population, if we know the sample parameters, then we can also estimate the population parameters from them. That means if I collect a sample and I see that the mean is of a particular value, then I can say that the overall population will have the same mean. And if I also collect the sample and it is more than number of 30, and we also check the standard deviation of the sample, then we can say that this standard deviation is equal to the standard deviation of the total population divided by the total number of the sample size. So from this we can actually say that the sample statistic can be used to estimate the population parameter. So we can, using this relationship, we can also determine that what should be the sample size in case we know the population parameters. That means if I know mu, if I know sigma square, then we can also determine the sample size that would be required to estimate our sample. So in this particular graph, we can see that this is the normal distribution that I was talking about, and this area under the normal distribution, this particular curve, which is a bell-shaped curve, houses around 34.113% of the observation, and so on the other side as well. So this is mean, this central line is mean, this is the average value, and all the observations are spread around the average value, and all these observations are lying around under this, more or less follows a normal distribution pattern, and we can say that within one standard deviation, around 34.13% on this side and 34.13% on this side. So that means around 68% of the data lies within one standard deviation. Similarly, within two standard deviation, around 68 plus another 27%. So that comes to around 99% of the data lies within this two standard deviation. and then we have got 3 standard deviation and 4 standard deviation and so on. So we can say that in 95% confidence level, out of 100 samples drawn from a population, 95 will provide an estimate within the fixed precision level or sampling error. So what it means is, I was explaining in a different way earlier. That means if in case we are drawing 100 samples, 95 of them will provide an estimate within the fixed precision level that we have defined earlier. That means if I have said that it is within a precision level of 5% or 2% on either sides, then 95% of the time it will be within this particular area. So in that way we can say that for sample size calculation, the confidence level desired is determined by the z value. Now z value is equal to x minus mu by sigma, which is nothing but this is the z score. So at mean it is 0, over here it is 1, that means it is 1 sigma away. So that means that observation is around the z score value over here is 1. So if I have around 68% confidence interval, then probably this is the value that we are looking for. If it is around 95% confidence interval, it comes to around over here, and if it is 99% confidence interval, then we are looking for a z score which is around over here, which is around 2.58, and this is 1.96. So 95% of the area under the normal curve is equal to z score of 1.96 over here, and 99% of the area under the normal curve is under z value of 2.58. So confidence interval says that that means for a particular precision value, we are sure that it will lie within this particular range of observations. So that means out of 100 samples drawn from a population, 95 will provide an estimate within the fixed precision level that we have defined, that is what is the sampling error level. So we can also have 99%, but that increases the precision further, that increases the confidence further. Now when we are talking about the population parameter estimation method, the term parameter is important, and here it means that these are the parameters of interest that we are talking about, and it belongs to the population. That means we either have to know the proportion of that particular of one attribute in the population, or we need to know its mean or the standard deviation for that particular population. So if I know these values, then we can estimate the sample size. So we don't need to know all of them. Some of them, if it is known, we can estimate the sample size. So if these data parameters are available, then it is okay. If it is not, there are certain strategies that we can follow. So what it means is, if I go for a sample survey in a town which I am not familiar with, for which we don't have any sampling frame. Sampling frame means that we don't have a sort of list where we know that okay, this is the list of people that are there in the town, so which is required for a random sample random sample set generation. So in that case, we can look for previous studies on this particular area or this particular population. If it is still not available, we can do a small pilot study and we can get estimates for mean or standard deviation, and even for proportion. That means we do a small sample which is much smaller than the actual sample size, and finding using the proportion of a certain of that particular attribute of interest that we are going to study, and we can see that proportion. From that we can also estimate its mean or standard deviation, and then we can use that in our in sample size calculation. Or it could be based on the experience. If we have a very experienced surveyor, then he can also use his experience to set this particular values for this particular population. Then we can use rule of thumbs. For example, if I know the range of the maximum value and the minimum value for that particular attribute, and we divide by 4, we get the standard deviation of that particular attribute. Or if we are doing a stratified random sampling or a strata-based sampling or a cluster-based sampling, we also need to have strata and other information or within that particular population. So these are the information that is required. And sample size calculation should be done using different methods. such as either through using proportion or using mean and standard deviation, and we should adopt the largest sample size that we get using this method, then we are on the safe side. But it is sometimes not practical. That means we cannot do all methods. In most cases, the proportion method is most appropriate, but we can also, if proportion is not known, we can go for mean and standard deviation, this kind of method. But usually we need to find out whichever gives the largest sample size, we should adopt that to be on the safe side. So once in case of simple random sampling, I'm not going for explaining detail of more complex sampling exercises like stratified random sampling or cluster based sampling. For only simple random sampling, which is in most cases we do simple random sampling, and we determine the sample size by different methods. The first method is determination of sample size for mean, and here for this method is apt for polytomous or continuous variables. Polytomous means a variable with multiple categories. That means we take an attribute which can be of different categories, whereas dichotomous means which has got only two categories, like for example male or female. These are two categories. But if I have age group, it could be of 4 or 5 categories. So it's polytomous. Now for polytomous could be also converted to dichotomous by adding up those different categories into broader categories and ultimately bringing it to dichotomous. And if it is dichotomous, then we can use a sample size based on proportion. That means this one is sample size based on mean, and we can determine sample size based on proportion. As I told you, it is a more robust method and will be explained in the next slide. So in case of determination of sample size for mean, the formula that is used is Nm equal to z square into sigma square by E square, where Nm is the sample size, Z is the z-score of the confidence level, E is the desired level of precision, and sigma square is the variance of the attribute or standard deviation, and which is basically means that the standard deviation has to be known, then only we can compute the variance. And sample size varies for each attribute, that I will come to later. So here we can say that z-score for confidence level 95% based on our previous. In this particular figure, I have shown the z-score for 95% is somewhere around here, because this is 95% of the observations are within this range. So here it is around 1.96. So that is why I have chosen 1.96. Let's take a standard deviation for this particular attribute as 5, and error value, that is the sampling error, we give a precision, we set a precision value as plus minus 10%. So that means we say that the estimate could be, if the actual estimate is 50, the estimate could be from 40 to 60. So that could be that kind of precision I am allowing. And Nm, so we estimate Nm is equal to, using the formula, and we see that the sample size comes to around 9,604 samples. So this is the sample size, number of samples that we need to collect using this particular method. So it is also clear that if I choose a different attribute of the population, instead of, like for example, I am doing a travel diary survey, if I take gender, then probably I will get a certain value because it has got a certain standard deviation, or it could be age, or it could be something else. It could be a continuous variable as well, like income levels. It could be continuous, and we can, if we know the standard deviation, we need to know the standard deviation, but different variables will have different standard deviations, that or the variances would be varying. So if the variance is different, then it will have a impact on the total number of samples that we need to collect. So that is the problem with using this method. Sometimes the sample size is varies by a huge margin. In one you may find the value is 1000, in another it may be around 15,000. So this is the range, this sort of variations can happen. So sometimes we can say that in the highest sample size should be adopted, as we have discussed earlier, but this method is, that's why, not that robust. Instead, the method based on proportion is more appropriate. So in addition to this, we should also be considering the non-response factor. That means a lot of people don't respond for back in a survey. That means we may approach them, but they may not be willing to participate in the survey. For that, we need to take provisions of extra samples that needs to be collected. So that will be taken care of by a non-response factor, which we can add to the sample size to get a higher sample size than the statistical estimate that gives us. So when we another popular when we do determine sample size for proportion, then one popular formula is Cochrane's formula for calculating sample size, and there are of course this is done when the population is infinite. That means the population is a huge number, and the formula that we use is ns equal to z square into p into q divided by e square. So here we take ns is of course the sample size, z is the z score value of the confidence level, and p is the proportion of the attribute in the population, and q is equal to 1 minus p. So this is where the variability is also coming in. So this is e square is the precision level, z square is the confidence level, pq is the precision variability. So instead of in the earlier formula, instead of variability, we were taking the standard deviation directly. So here we are taking variability of the population. P is the proportion of the attribute in the population, and q is the 1 minus p, the remaining part. So here in the estimate, if I say a z score for confidence interval, if I take a confidence interval of 90%, then the z score is around 1.645, and p value is equal to 0.5. We take 50% variability, which is the maximum variability possible. Then q becomes 0.5. Error is, we have taken plus minus 5% on both sides. Now this is converted into this is percentage. This has to be written like 0.05, and we put all these values in the equation, and we get ns equal to around 270 samples. So that also means that if I increase the error to 10%, the sample size will reduce. If I reduce the variability, then also the sample size will reduce. So in this one, but at the same time, if I increase the confidence level from 90 to 95% or 99%, then the sample size will increase. So here I can show you that z score for 99% confidence interval is equal to 2.58. So we have increased the confidence level, and we have reduced the variability level by saying p is equal to 0.8 and q is equal to 0.2. So 80% and 20%, that is the variability. Error we keep as same. We see that the sample size has increased to around 426. So this also means that the impact of confidence level is pretty high compared to variability. So the previous formula by Cochrane actually talked about when population size is infinite. But if I have a finite population size, that means we have a large population, but it's still finite, and we say that that means if the sample size estimated is more than 5% of the total population, then we need to incorporate a correction factor which can reduce the sample size. That means Cochrane also suggested that a finite population correction factor needs to be introduced if the population is of finite size, and it is given by n equal to ns divided by 1 plus ns minus 1 divided by caps n in caps, where n in caps is equal to the total population and ns is equal to the sample size determined using Cochrane's formula for infinite population. So using this, if I assume that the total population of a city is around 50,000, and based on the previous calculation, like we did over here, and like for z score of 99% confidence interval, which is 2.58, and variability of 0.5, e value of plus minus 2%, we say that the total number of population that samples that we need to collect is 4160. So this population is approximately 8.3% of the total population. So by rule we can say that, by a thumb rule we can say that if the sample size estimated is more than 5% of the total population, then only the correction factor is utilized. So because it is 8.3%, we utilize we add the correction factor, and when we do the estimate for correction factor, we find that n reduces to 3851, which is the new sample size. So that means if my sample size is infinite, then probably the total number of samples collected is a little less. So similar to the previous formula, in Yamane also proposed another formula where directly we can use population instead of the variability in the population. So here we can say that if we consider a confidence interval of 95% and the proportion of attribute of the population we consider this as fixed at 0.5%, then then the Yemen's formula states that NT is equal to n in caps divided by 1 plus n caps n into E square, where n is the population, E is the level of precision, and NT is the sample size. So this is a very simple formula that also could be used, and if I put n equal to 50,000 with a E value of plus minus 2, then we find that the total sample size required is 2381. Whereas if I use error estimate or a precision value of around plus minus 5%, then we get a error value of a sample size of 397. So you can see that increase in the precision increases sample size by a huge order. So we need to be careful what is the appropriate precision that we require. So in certain studies the precision level required may not be that high, so we can go for a 10% precision level. So it depends on what kind of study that we are doing. Finally, to conclude, we can say that for what we discussed till now is about the methods of sample size collection is for only random sampling, whereas for stratified random sampling we need to also consider not only the variances of the population but the variances of each subpopulation, the different stratas that are there or the clusters that are there, along with variability in the total population. So these are the things that we need to introduce, we need to study. So there are some new factors that gets introduced into the equation, which is called a depth factor, and this actually takes care of the sample of the subgroup variances and so on. So that could be, these are more complex sample designs, but overall if we have a larger area and if we have a urban area and we are doing a travel diary survey, we can go with the previous formulas that we have estimated, that I have shown in the earlier slides. And sample size also is not, many people have designed different formulas for sample size. That means there are no very hard and fast rules for determining sample size. It has to be dependent on the analysis that we are doing. So if we are estimating only mean and frequency of a particular variable from the sample that we are collecting, then the sample size could be much smaller. It could be of any size more or less. Whereas if we are doing detailed analysis, like we are doing regression analysis, we are trying to see how each of the exploratory variables impact the dependent variable, and we need to find those relationship, or we are doing analysis of variance. In that case we require more number of samples, where around approximately 200 to 500 samples could be appropriate. Like for logit regression, we have a standard thumb rule for around 350 samples that we need to collect. So these are the different rules, straightforward thumb rules that we can also use. And it could be also, as we have seen, that if the data is distributed normally, then we can have a less number of sample size, like around 30 to 200 for any kind of estimates. Whereas if the distribution is skewed, that means if the distribution looks something like that instead of a normal distribution which is more or less uniform, then you can understand that we will require probably more samples in case of a skewed distribution. So these are the different aspects that also influences sample size. So these are some of the references you can use for studying sample size. And to conclude, we can say that various methods and rule of thumbs are followed for sample size determination. In addition to population characteristics, sample size depends on desired degree of precision and confidence level required by the surveyor. So that means that the more precise I want my results, more would be the sample size, and also confidence level, if it increases, then also we require more sample size. And sample size determination based on proportion is more robust compared to sample size determination using population variance. And finally, sample size also depends on the type of analysis and the distribution of the data. Thank you.